Good afternoon, guys. To start off your notes today, we are going to start setting up a little booklet for your notes. You should have two pieces of paper that are marked Chemical Equations Notes. Okay? Let's start with the page that looks like this. It says page 1 at the bottom. You'll notice that they are printed front and back. So we're going to go ahead and fold this piece of paper in half like a book. We want page 1 to be on the outside of our book, so like this is the cover, and then on the outside back of our book we've got page 6. If you open it up to the inside, there's page 2 on the left and page 5 on the right. We're going to set that one aside. You're going to look at your second page. This is the one that says glue this side to your notebook, and it's got page 3 on one side, pages 4 and 7 on the other side. We're going to fold that in half so that page 3 is on the outside of your booklet. So go ahead and fold it like that. We've got page 3 on the outside. We've also got the side that says glue this side to your notebook on the outside. And if we open it up, we've got page 4 and page 7 on the inside. So here's the trick for this one. To make a booklet without using any staples or glue or tape, we're going to take our pair of scissors. I'm going to take my page 1 booklet. Okay, so this is the one that says page 1. And on that line we just folded, before I cut anything, I'm going to show you. We're going to cut about an inch here along this line and about an inch at the top. So here's what that looks like when I cut. Watch before you cut. I'm going to cut just about an inch there. So I've got a little flap now. I'm going to turn it around and cut about an inch on the top. Okay. So now it's cut on both sides, but it's not cut all the way down. Okay, we're going to take that and set it aside. On this second page, this is the one that says page 3 on it, I'm going to cut just a little bit. I'm not going to start at the edge. So I'm going to go in about an inch. I'm going to cover that with my finger so I don't cut it. I'm going to cut just a little tiny bit there. When I open it up, I can stick my scissors in that little hole I just made. You need a slightly bigger hole. So open up that paper. Got a little hole right here. I'm going to stick my scissors in there. I'm going to cut down the middle of this page, leaving about an inch of paper at the top and at the bottom. So I'm cutting almost all the way down, and right about here I'm going to stop cutting. I'm not going to cut any further than that. Okay? So if you look, I can open it like that, but it's still attached at the top and the bottom. Alright? So, last thing I'm going to do, I'm going to take the page that has the cuts at the top and the bottom. I'm just going to bend it in half. I'm not going to crease it because I don't want to actually fold this one. I'm going to open up the page that I cut the middle out of so that I've got pages 4 and 5. So it's open, like we've opened our book. And I'm just going to slide page 1 in through this hole. Okay. And then unfold it. And like magic, I've made a book. I'm going to crease that nicely. Now when I open my book, I should see page 1. Flip it open. Page 2, right here. Page 3, 4, 5, 6, and 7. And then on the back cover of my book, that's the part that says glue this side to your notebook. Okay? If you missed a step of that, please back up the video and watch it again. Please watch the instructions all the way through before you actually cut anything, or else you're going to be having to tape this back together. Okay? So now that you've got your notes booklet, we're going to start on the actual notes. So for our notes today, we're going to be starting chemical formulas and chemical equations. So the reason that scientists use chemical formulas and chemical equations instead of just drawing out the molecules is that works okay if you have something small. So for example, if I wanted to draw out a molecule of water, I've got my oxygen, and then I've got 2 hydrogens attached to it. That one's easy to draw. But there are some other ones that would not be so easy. So for example, I drew this one out ahead of time. This is glucose, and it is a little bit more complicated. And if we had to draw that every time we wanted to talk about the chemical formula for glucose, and glucose is used a lot because it's something your body needs to survive, that would just take too long. So what we do instead is we create a chemical formula. So we're going to start filling in the blanks in our notes. So instead we create a chemical formula that shows us what elements are present and how many of each of them there are. Okay? So each element in that formula is represented by its elemental symbol. Oops. Elemental symbol. From those elemental symbols, I've given you a few examples on your notes, some of the more common ones. These are the ones that you see on the periodic table, so those 1 or 2 letter abbreviations. We've got C for carbon, O for oxygen, H for hydrogen, N for nitrogen, and Na for sodium. So they could be 1 letter or 2 letters. If they're 2 letters, there's always a capital and a lowercase letter. If they're just 1 letter, it's only a capital. Okay? The number of each element is shown by the subscript to the right of it. And you might remember that from your workbook pages last week. So if a subscript, which is just a little number, and you'll see some examples of those in a second, if there is no subscript, then you're going to assume that there's only 1 of that atom. So if you see a little number next to one of your elemental symbols, so if it says N2, that tells you that there's 2 nitrogens. If you don't see a number, if all you see is an N, then there's only 1 nitrogen. Okay? So I'm going to flip my page. This should be on the same page for you. And we're going to practice with some chemical formulas. So I've given you a bunch of examples along the left here. So we're going to count how many of each atom that we have, and we're going to draw our example to go alongside it. So I'm going to start by circling in my formula which different atoms I have. So I've got a C right here, a capital C. So that's carbon right there. And then I've got an O2. So I'm going to circle the O and the 2 here. Okay. So I have carbon, which is a C. And I've got oxygen, which is an O. And I don't see any number next to carbon, so from my notes that I just did, if I don't see any subscript, I'm going to have 1 carbon atom. I see a little 2 next to oxygen, so I know that I've got 2 oxygen atoms. So if I was going to draw out this molecule, I would draw 1 carbon, I'm going to label it, and then 2 oxygens. Okay? So I can count on my visual model. 1 carbon, 2 oxygens gives me CO2. Okay? Let's try another one. On this one, I've got Cl2. So I've got a capital C and a little l. That's an L, not an I. If it was an I, it would have the crossbars on the top. So Cl2. Cl is my symbol for chlorine. So this is telling me that I've got some chlorine. And there's only 1 element here because I only have 1 elemental symbol, just the Cl. So I've got the subscript of the 2 right here, so that tells me that I've got 2 chlorines. Alright, I'm going to try another one. This next one I've got NH3. So I've got a capital N and a capital H, so those are two different elements. The N doesn't have anything next to it, so I'm just going to box that in. And then the H has a 3 that goes with it, so I'm going to include that in my box. So N, from your notes, is nitrogen, and then H is hydrogen. So if I have no subscript, no little number next to my N, that tells me there's only one N. And if I have a 3 next to my hydrogen, that tells me that there's 3 hydrogens. And we forgot to draw our example for the last one. It was so easy, I forgot about it. We've got 2 chlorines next to each other. For this one, I've got 1 nitrogen. I'm going to draw that in pink. And then I've got 3 hydrogens attached to it. I'm going to label my little hydrogens. Okay? Next one. This one has a capital N and a little a, and then a capital C, lowercase l. So we just said that Cl was chlorine, so I'm going to box in that chlorine. And then Na is the symbol for sodium. So I'm going to write sodium and chlorine. I don't have a subscript next to either of them. So how many of each do I have? Hopefully you said that we only have one of each. We've got 1 sodium and 1 chlorine. If you remember from last week, NaCl, sodium chloride, is actually an example of an ionic bond. So we've got our Na and our Cl. Sodium chloride is table salt. And then this NH3 is ammonia. We've got chlorine gas and carbon dioxide. Okay, let's try a little bit trickier one. This one has 3 that go in it. So we've got C2H4O2. So I've got 3 separate elements, 3 separate capital letters. I've got C2, so that's carbon. I've got H4, which is hydrogen. And notice that I'm always boxing in the subscript that goes next to our element. Last we have oxygen. Okay, so there's a little 2 next to my carbon, so that tells me I've got 2 carbons. There's a little 4 next to my hydrogen, so I've got 4 hydrogens. And there's a little 2 next to my oxygen, so I've got 2 oxygens. So how many atoms total do I have in this molecule? I've got 2 carbons plus 4 hydrogens plus 2 oxygens gives me 8 atoms total. Okay? So 2 plus 4 plus 2 gives me 8. And what that one looks like we've got our 2 carbons, and then 3 hydrogens over here, and 2 oxygens, and another hydrogen. So that one's a little bit more complicated. You might understand why we don't want to draw that one out every time. We just like to use the shortcut, the formula. Okay, so C2H4O2, that's acetic acid. That's what you find in vinegar. Alright, last one, we've got NaHCO3. So this is a longer one. How many elements do we have in this formula? How many capital letters? I see 1 here, so we've got Na, right here. We've got an H right here. We've got a C. And then we've got an O3. So 4 different elements in this one compound. So Na was sodium. Draw a line to separate these. We've got H for hydrogen, C for carbon, and an O for oxygen. So what's my subscript on sodium? Do I have a subscript here? Do you see any little numbers? Hopefully you say no, or else you need to get your eyes checked. We've got no subscript, so we've only got one sodium. We've got no subscript on our H, so we've only got one hydrogen. Still no little numbers on carbon, so there's only one of those. But I do have a subscript over here on oxygen. I've got a little 3, so that tells me I have 3 oxygen. So for total number of atoms over here, I've got 1 plus 1 plus 1 plus 3. So this one has 6 atoms total. I've got 1 atom of sodium, 1 atom of hydrogen, 1 atom of carbon, 1 atom of oxygen. And all together, they form another ionic compound. So we've got our sodium, our carbon, wrong color there, 3 oxygens, and a hydrogen. So for us, it would be much easier to just write out the formula than it would be to draw these guys every time. Just because the simple ones are easy to draw doesn't mean that it's easy to draw all of them, especially when you get into bigger molecules like sucrose and glucose and carbohydrates. We want nice short formulas for those instead of having to draw pictures. Alright, so we can represent different molecules with chemical formulas. And one of the things that we use those for most often is when we're writing chemical equations. So when I have a chemical reaction, when I have 2 compounds or 2 atoms that are reacting with each other, they are producing something new, and I can write that out as a chemical equation. So chemical equations are used to represent chemical reactions. The left side of my equation shows the reactants, which are the materials that are doing the reacting. They're the stuff that you start with. So your reactants are going to be on the left of your equation. You're going to have an arrow in the middle, which means yields. So your reactants yield your products, or they make your products. If you see an arrow, that's your sign that your reaction's taking place. Okay? And then on the right side of the equation, we've got the products. So the reactants are the stuff that you start with originally. You got an arrow in the middle that says, hey, something's happened here. And then on the right, you've got the stuff that you end the reaction with, your products of your reaction. So looking at an example of a chemical formula or chemical equation, we've got our chemical equation. Let's do a simple one. We'll do carbon plus 2 oxygen, got an arrow in the middle, and my product is CO2, or carbon dioxide. So what that looks like, if I was going to draw this out, I've got 1 carbon plus 2 oxygen. Okay, 1 carbon plus 2 oxygen gives me carbon dioxide, which is carbon and 2 oxygens all bonded together. Okay, if I was going to write this out in words, I would say 1 carbon plus 2 oxygen yields 1 molecule of carbon dioxide. So 1 carbon plus 2 oxygen yields 1 molecule of carbon dioxide. Okay? So one of the ways you can count how many reactants you have is you can look for the plus sign. Every time you see a plus sign, you've got a new reactant. So I've got one guy over here and a plus sign and another guy over here. And I could keep adding plus signs and reactants if this was a more complicated equation. Okay? So the last thing we're going to do is we're going to count how many of each atom I have on each side. So over here on the reactant side, if I just look at my visual model, I've got 1 carbon and 2 oxygen. And if I look over on the right side of my arrow, I've still got 1 carbon and I've still got 2 oxygen. Okay? So 1 carbon on this side, 1 carbon on this side, 2 oxygen on the left, 2 oxygen on the right. I'm going to switch pages here. So on that example, you saw the number of atoms on the reactant side and the product side stays the same. And there's a law for that in chemistry. We call that the law of conservation of mass. So the law of conservation of mass says that you start and end a reaction with the same number of atoms. Nothing is created, nothing is destroyed, we're just changing things around, and everything that we had at the beginning, all the atoms we had at the beginning, are still there at the end, they're just bonded differently. Okay? So we haven't added any new atoms, we haven't taken away any atoms, they're still there, they've just been rearranged. That's what the law of conservation of mass says. So when you make sure that both sides of your equation have the same number of atoms, we call that balancing the equation. Okay? So basically when you're balancing an equation, all you're doing is counting the number of atoms on each side. So you want to make sure that if you started with 5 carbons, you end with 5 carbons. If you started with 3 hydrogens, you end with 3 hydrogens. You're not always going to get balanced equations at the beginning. Sometimes you have to balance them yourself. So to balance an unbalanced equation, you're going to change the coefficient, C-O-E-F-F, I'm going to try rewriting that. C-O-E-F-F. There we go. We're going to change the coefficient in front of the formula. So the coefficient is the big number in front of an atom or a formula. So we said subscripts are the little number, coefficients are the big number. You'll see that in a second. Subscripts, when you're balancing an equation, cannot be changed. They are off limits. The subscript represents how many atoms you have in a molecule. The coefficient tells you how many molecules you have. Okay? So subscripts tell you how many atoms of a molecule you have. Coefficients tell me how many molecules I have. Okay? And same rule as for subscripts. If you don't see a coefficient, if I just give you a molecule with no number out in front of it, you're going to assume that there's just one of them. Okay? So starting with that, I'm going to draw out my examples. If I just had CO2, okay, same example we just did, that means I have 1 carbon and 2 oxygens. Okay? If I put a 2 out in front of my CO2, then I've got 2 molecules of carbon dioxide. I've got 2 of this whole thing right here. So I'm going to draw that out again. But instead of having 1 carbon dioxide, I'm going to have 2 carbon dioxides. Okay? If I put a 3 out in front of it, now instead of having 1 carbon dioxide or 2 carbon dioxides, now I've got 3 carbon dioxides. If I put a 4 out in front of it, then I'd have 4 whole molecules of carbon dioxide. Okay? So one thing I want to do real quick is count how many atoms I have in each of these situations. So in this atom, I have 1 carbon, or in this molecule, I have 1 carbon, and I have 2 oxygen. Okay? Over here, I've got 2 purple carbons. I have 2 carbon dioxide, so I have 2 purple carbons, and then I've got 1, 2, 3, 4 oxygens. Okay? We'll keep going over here. I've got 1, 2, 3 carbons, and I've got 1, 2, 3, 4, 5, 6 oxygens. And then last over here, I've got 1, 2, 3, 4 carbons, and 2, 4, 6, 8 oxygens. Alright? So what pattern are we seeing here? When we increase the coefficient, how does that increase the number of each atom that we have? Alright? We're going to practice a little bit with that. So I'm going to give you some formulas. So we're going to start with H2O, and then we're going to do NH3, and then H2O2. So we've got water, ammonia, and hydrogen peroxide. And in front of each of these formulas, I'm going to put a coefficient. So we'll put a 2 there, and a 3 here, and another 3 right there. And I'm going to start counting how many of each atom I have. Okay? So we'll actually start by drawing them, I think. So starting with our water molecule, I've got 1 oxygen and 2 hydrogens. So I'm going to draw my oxygens in blue and my hydrogens in green. And my coefficient tells me that I've got 2 water molecules. So I've got 2 of those guys. So I'm going to count how many hydrogens I have, and I'm going to count how many oxygens I have. So if I look over at my visual model, I've got 2 blue oxygens and 1, 2, 3, 4 blue hydrogens. Another way that I could find that is I could look at just the formula, because we're not always going to draw them out, right? I'm going to look at just the formula and I'm going to say, okay, if I ignore my coefficient, I've got 2 hydrogens and 1 oxygen, but then if I see that coefficient there, I have 2 of each of these now, so I need to multiply by 2, and this is an O, not a 0. Okay? So if I multiplied by 2, then I would actually have 4 hydrogens and 2 oxygens, and that matches what I saw over here on my visual model. Let's practice that again. So we're going to jump down here to our NH3, our ammonia, and if I draw this out, I've got 1 N for every 3 H's. So I've got an N and then 3 hydrogens on that. My coefficient tells me I need to draw that 3 times. So I have 1, here's my second, and my third. I'm going to draw that out. Okay. Now we're going to count how many of each that I have. So if I took my coefficient, I would have 1 n. So 1 n for every excuse me, for every 3 h's. Okay? But I don't just have 1 n and 3 h's. My coefficient tells me that I have to do that 3 times. So I'm going to multiply by 3 on each of those. So 1 n times 3 gives me 3 n's. 3 h's times 3, 3 times 3 gives me 9 h's. And if I come over here and I count, I have 1, 2, 3, 4, 5, 6, 7, 8, 9 h's, and 1, 2, 3 n's. Okay? The last one we're going to do today, we've got h's and o's again. So H2O2, hydrogen peroxide. If we draw that out, if I just cover that up, I've got 2 h's and 2 o's. So I'm going to draw my 2 o's and add my 2 h's. And my coefficient tells me I need 3 of those. I'm going to draw 2 more. Okay? So if I was just looking at one of these, if I just cover that up, I'd have 2 hydrogens, because my subscript says 2, and I'd have 2 oxygens, because my subscript says 2. Okay? But I've also got a coefficient in front, so I need to multiply them both by 3. And if I do 2h times 3, that gives me 6h. If I do 2o times 3, that gives me 6o. Not 60, 6o. Alright? So to summarize what we just did here, to find out how many atoms of an element are in the formula, you have to multiply the coefficient and the subscript together. Okay? So I'm going to take my subscript and my coefficient and multiply them together. So when we said we had 2 hydrogens in one molecule, and we had 3 molecules of that, that gave me 6 hydrogens. So that was my big number 3 times my subscript 2. I did the same thing for oxygen. Big number 3 times the subscript 2 on oxygen. When I was up here working with ammonia, NH3, I had my big 3 times my subscript on N, and I don't see a subscript, so that was just a 1. So 3 times 1 was 3. And then I had to do 3 times my subscript on H, which was 3, so 3 times 3 was 9. Alright? So that's how you count how many atoms you have if you have a subscript and a coefficient. And remember, if there's no coefficient in front, that means you just have one of these molecules. Okay? So we're going to practice balancing an equation now. So if I gave you an equation that wasn't balanced, and I ask you to balance it for me, here's what we're going to do. So our example equation is going to be N plus H makes NH3. Okay? N plus H equals NH3, or yields NH3, because this isn't an equal sign, it's a yield, this arrow. Alright? So how many of each atom do I have over here? I don't see any coefficients or subscripts on this side. So no coefficient in front, no subscript on the side means I only have one of these n's. So I have one N on this side. Same thing with the H. There's no number in the front. There's no subscript on the right. So I've only got one H. Okay? Coming over here, I don't have any subscripts in front. I don't have any subscript next to my, or I don't have any coefficients in the front. I don't have any subscripts next to my N. So I've only got one N over here. I don't have any subscripts in the front, but I do have a coefficient, or a subscript. Excuse me, let me try that again. I don't have any coefficients in the front, but I do have a subscript on my H. So I'm going to have 3 H's. Okay? So if I drew out a visual model of that, I've got 1 nitrogen plus 1 hydrogen gives me 1 molecule of ammonia, NH3. Okay? So just looking at my model, or looking at how many of each I have, I've got the right number of nitrogens on both sides, but I've got 3 hydrogens on the right, on the product side, and only 1 hydrogen on the left. So what can we change to get 3 hydrogens on the left? If you flip back in your notes, because I know some of you just said subscript just now. If you flip back in your notes, you saw that the subscripts are off limits. I've given you this equation. You cannot change the subscript. So what I need to change instead is the coefficient in front of the H. Okay? So I need there to be 3 of these hydrogens. So when I'm writing out my equation, I'm going to change this subscript from this coefficient from a 1, which is what it is right now, even though you can't see it. That's a 1. I'm going to change it from a 1 to a 3, and then we're going to count again. So this time I'm going to have N plus 3H yields NH3. Okay? The question at the bottom says, is this balanced now? So we're going to count again. I've got no coefficient and no subscript on my N, so I've got 1 N on this side. I've got no subscript and a coefficient of 3 on my H, so 3 times 1 gives me 3H. On the other side of the arrow, you can draw a line down here if it helps you separate these two sides. I've got no coefficient in the front, no subscript on the end, so I've got 1 N, and I've got no coefficient in the front, and a subscript of 3 on the H, so that would be 1 times 3 gives me 3H. So are my numbers the same on both sides? I've got 1 N on the left, 1 N on the right. 3H on the left, 3H on the right. Is this balanced now? The answer is yes. Alright. Let's try another one. So we've got chemical equation is going to be P4. So P stands for phosphorus. We've got 4 phosphorus plus O2, 2 oxygen, gives me P4O10. Okay? So we're going to count atoms on both sides. On this side I've got a no coefficient, subscript of 4, so 1 times 4 gives me 4 phosphorus. I've got no coefficient and a subscript of 2, so 1 times 2 gives me 2 oxygen. I'm just going to write that out so it doesn't look like 20. On the right, I've got no coefficient, subscript of 4, that gives me 1 times 4 is 4 phosphorus. No coefficient in the front, subscript of 10 on the oxygen, 1 times 10 gives me 10 oxygen. Okay? Clearly something's wrong here. I've got 2 oxygen over here, 10 oxygen over here. My phosphorus is balanced. I've got 4 on both sides, but I'm short on oxygen right now. So the next question asks, what are the reactants? So remember, reactants are what you're starting with in your equation. So it's the stuff on the left. Your reactants in this case are phosphorus and oxygen, or P and O. Okay? And my product on the right hand side, we're going to put the subscripts on those just so we don't get confused, is P4O10. That molecule, that whole molecule, is my product. So to get 10 oxygen on each side, I have 2 oxygen over here. I can't change that subscript. So whatever I put in front of that oxygen is going to have to get multiplied by 2. So what can I multiply by 2 to make 10 is the question that I need to ask myself. What coefficient can I multiply by 2 to get 10 oxygen? Coefficient that I came up with there is 5. So let's count our atoms. We've got 1 times 4 gives me 4 phosphorus over here. I've got 5 times 2 gives me 10 oxygen over here. On the other side of this equation, I've got 1 times 4 gives me 4 phosphorus over here. 1 times 10 gives me 10 oxygen on the right, on the product side. So is this equation balanced now? The answer is yes. Alright, we're on the next page now. We're going to try a slightly harder example of what we were just working on. So my chemical equation this time is going to be N2 plus H2 yields NH3. So let's start by counting our atoms. I've got 1 times 2, my subscript. My coefficient is 1 because I don't see any numbers there. So 1 times 2 gives me 2 nitrogen. Same thing over here, no coefficient, so that's a 1 times 2 hydrogen gives me 2 hydrogen. On this side, no coefficient, so that's going to be a 1. No subscript next to N, so it's going to be 1 times 1 gives me 1 nitrogen. My coefficient is 1. My subscript on H is 3, so 1 times 3 gives me 3 hydrogen. So on this one, none of my numbers on the left and the right are the same. I've got 2 over here, 1 over here, 2 over here, 3 over here. So on this equation, we're going to have to change coefficients on both sides of my equation, on my reactant side and on my product side, to get that equation balanced. So we're going to start by trying to get my hydrogens balanced. I've got 3 on the product side, I've got 2 on the coefficient side, and I need them to be the same. So the way that I'm going to do that, remember I can't change my subscripts. Those are off limits. So I need to find something that I can multiply both of them by so that I end up with the same number on both sides. So that something that I'm looking for is the lowest common multiple. You might remember that from your math classes. So to find the lowest common multiple of 2 and 3, I'm going to start by listing out the multiples of 2 and 3. And remember, listing out the multiples, we're basically just counting by that number. So multiples of 2, we're going to count by 2's. So I'm going to start by making a list. We've got 2, 4, 6, 8, 10. We'll stop there. And then we're going to list out the multiples of 3. So count by 3's. We've got 3, 6, 9, 12, 15. And my lowest common multiple is going to be the first number that I see that's on both lists. So 2's not on both lists, 3's not on both lists, 4's not, but 6 is. So I've got 6 on the first list and 6 on the second list. So my lowest common multiple that's on, my lowest number that's on both lists is going to be 6. So what that means is when I go to balance my equation and I count my atoms, I should have 6 hydrogens on both sides. So to get 6 hydrogens on the reactant side, looking over here on the left, on my reactant side, I have 2 in my subscript. I need 3 hydrogens total, so what can I multiply by? I need 6 hydrogens total, so what can I multiply by 2 to get 6? And the answer to that is 3. So if I multiply 2 and 3 together, I get 6. So I've got 2 H's on the left. I need 6, so I'm going to multiply by 3. So 2 times 3 equals 6 H's. That means my coefficient is going to be 3. So it's going to be 3 H2 on the left, on the reactant side. Okay? I want the same number on the product side. I want 6 hydrogens on the product side as well. And remember, on the product side, I've got a different subscript with H. I've got a 3 with H. So what can I multiply by 3 to make 6? So to do that, I'm going to multiply by 2. So my coefficient on the right, on the reactant or the product side, is going to be 2. So I started with 3H. I need 6. So I'm going to multiply by 2, which means my coefficient is going to be 2. Okay? And remember, on the reactant side, when I'm looking at that molecule, it's not just H3, it's NH3. So I'm actually going to have 2 of that whole molecule, so 2NH3. Okay? So we're going to put those coefficients back into our chemical equation, and we're going to count again. So I didn't do anything with the N on the reactant side, so I'm going to leave it the same as it was. I had 3 coefficient on my hydrogen on this side, so 3H2, and that yielded 2NH3. So we're going to count our atoms one more time. I've got a 1 in front of my N on the left. I've got a 2 in the subscript. 1 times 2 is 2 nitrogens. I've got 3 times 2 to find the number of hydrogens. That's going to be 6 hydrogens. Over here I've got 2, no subscript on the end, so that's going to be 1. 2 times 1 gives me 2 nitrogens. 2 times 3 for hydrogen gives me 6 hydrogen. So looking at both sides, I've got 2 nitrogen on the left, 2 nitrogen on the right, 6 hydrogen on the left, 6 hydrogen on the right. My equation is now balanced. Alright, moving on to our last example. This one's going to be a little bit tougher, so I've called this one a challenge problem. This is not something you'll be expected to do on your everyday test, but it would be something more like a bonus question. So for this one, the equation that I'm going to give you here is H2O2 yields H2O plus O2. Okay, so hydrogen peroxide yields water plus oxygen. So for this one, we're going to count how many atoms we have. I'm going to switch colors so that's more visible. On the left, we've got 1 in front, 2 in the subscript, so 1 times 2 gives me 2 hydrogens. Same with the oxygen, 1 in the front, so I don't see anything, so that's a 1, times 2 next to the oxygen gives me 2 oxygen. I'm going to write OXY because I don't want it to look like a 20. On the right, we've got 1 in front of the water, so 1 times H2, 1 times 2 gives me 2 hydrogens. 1 in the front, because I don't see anything, don't see any subscript, so that's another 1, so 1 times 1 gives me 1 oxygen. Okay? But I've also got more oxygen over here. I've got no subscript in front of, or no coefficient in front of it. I've got a 2 in the subscript, so 1 times 2 gives me another 2 oxygen. So all together, on this right side of the equation, I get 1 oxygen from the water, I get 2 oxygen from the oxygen gas, so all together I've got 3 atoms of oxygen on the right. So I've got 2 hydrogens on the left, 2 on the right. Those are balanced, but I've got 2 oxygens on the left and 3 oxygens on the right. Those aren't balanced. So what I'm going to do, there's not anything obvious here that I can change right away to get those oxygens balanced. I know for sure that I need to increase the number of oxygens that I have on the left. Okay? Can't change any of the subscripts over here, so I can only add coefficients. So I've got to start by increasing the number of oxygen I have on the left. So we're going to, let's say we'll double it to start with. So I'm going to put a 2 coefficient in front of my H2O2, my hydrogen peroxide. And then we're going to count atoms again. I'm going to go a little faster this time since we're on the challenge problem now. You've had some practice with this. Now we've got 2 coefficient, 2 subscript, 2 times 2 gives me 4 hydrogens. Same with the oxygen, 2 coefficient, 2 subscript equals 4 oxygen. On the right, nothing has changed, so I can just carry down those numbers from above. I have 2 hydrogen and 3 oxygen. Okay? Now nothing's balanced. I've got 4 hydrogen on the left, 2 on the right. I've got 4 oxygen on the left, 3 on the right. So what am I going to do here? Well, I need 2 more hydrogen and 1 more oxygen. So if I look at my equation, there is actually something I can change here that would give me 2 more hydrogen and 1 more oxygen. There's no hydrogen over here, so I'm not going to touch that O2. But if I doubled the amount of water that I have, that would give me 2 more hydrogen and 1 more oxygen, which is what I need. So we're going to change the coefficient on that water molecule. We have our 2 H2O2 on the right, and then, or on the left, and then on the right, we're going to double the amount of water that we have. We're going to count atoms again. Nothing changed on the left from step 1, so I'm just going to bring down those numbers. 4 hydrogen, 4 oxygen. On the right, I've still got 2 oxygen from the O2. I've got 2 in front of the H2O, so 2 times 2 in the subscript for H gives me 4 H's. And then no subscript on the oxygen, so that's a 1. So 2 times 1 gives me 2 more oxygen. So all together on the right, if I look, I have 2 oxygen up here, 2 oxygen up here. If I add those together, I've got 4 oxygen. Okay? So looking at the left, got 4 oxygen, 4 hydrogen. On the right, 4 oxygen, 4 hydrogen. So is this equation balanced now? Your answer is yes. So that's a more complicated one that you're going to see. Alright. Last thing we're going to look at, just a couple more terms to know. One of the things I want you to know is that there are 3 main types of chemical reactions, 3 main patterns that you'll see. So the first one that you're going to see in a synthesis reaction, you've got multiple reactants on the left combining to form a single product on the right. So what that looks like is that I've got something, I'm just going to say A, plus something else gives me a single product of those two things just combined together. So A plus B equals AB. What that looks like in an actual example would be something like creating ammonia. So 2N2, this is an example that we did earlier, plus 3H2 makes 2NH3. So I had two products on the left, two reactants on the left, one product on the right. So if you ever see a reaction that has a plus sign on the left and no plus sign on the right, that's a synthesis reaction. The opposite of a synthesis reaction is a decomposition reaction. So in a decomposition reaction, it's the reverse. You've got one thing on the left and it breaks down and forms multiple products. So what that looks like in the general example is exactly the opposite. You've got the product that we made in the first one, AB, breaking down into A plus B. And an example of that reaction would be the breakdown of water. So if we started with 2H2O, it would break down into 2H2 plus O2. So in a synthesis reaction, the plus sign's on the left of the arrow. In a decomposition reaction, the plus sign's on the right of the arrow. And then your last type of reaction that I want you to know is a replacement reaction. And in this reaction, you've got multiple reactants on the left. They switch atoms and form new products, multiple products on the right. So in a replacement reaction, you're going to have plus signs on both sides of your arrow. I'm going to need a couple more colors for this one. So in a replacement reaction, we'll keep going with the example I already had. We've got AB plus some other reactant, CD, and what they do, they just switch those atoms around. So A and B were together on the left, they're going to be split up on the right. Same for CD. So same atoms all the way across, they've just switched places. One example of that would be combustion of methane. So we've got CH4 plus 2 oxygen and when that combustion reaction happens, they break down into carbon dioxide and water. We've got 2H2O. So you just see the carbon was with the hydrogen over here. On the right side it's with the oxygen. On the left the hydrogen was with the carbon. On the right it's with the oxygen. So they just switched places. They just switched partners. Alright, last part of your notes. 2 words I want you to know. 2 big vocab words. Some reactions involve heat. When you're making or breaking chemical bonds, it can create heat or it can absorb heat. So remember that heat is just a form of energy. So bonds, chemical bonds, is one of the ways that energy gets stored in nature. And when you make bonds or break bonds, you can release some of that energy. Or for some reactions, they need energy, so they have to have heat to be able to start. So if a reaction produces heat, meaning that it feels hot, then we call it an exothermic reaction. So exo means out, thermic means heat, so it's putting heat out. It feels hot. Okay? If it's one of those reactions that needs heat to get started, it's going to absorb heat and it's going to feel cold. And when it feels cold, we call that an endothermic reaction. So endo means in, thermic means heat. It's taking heat in, it's sucking in the heat from around it, and it doesn't leave anything behind, so it feels cold. Okay? I know these were long notes. Thank you for sticking with me. If you missed anything, please go back and fill them in. You will need to know all of this to understand what we're going to be doing for the next couple of weeks. Please practice with these chemical equations. You'll be getting plenty of opportunities to practice with them. If you have any questions, please let me know in class. Have a good day.